season if you don't keep on top of them. So he felt that he still had to spray every acre, every year in many of his crops, regardless of how low the weed densities were. And so I guess the realisation for me at that point in time was that, well, unless we've got some way of actually specifically targeting the individual weeds that are out there in that paddock, you're never really going to realise the benefits of low weed densities in your production system. And so that's the reason why we started looking at in-crop site-specific weed control. Okay, so what does that opportunity look like? Well, saving money, obviously. So if you start targeting weeds, then you can reduce your weed control costs quite substantially, depending, of course, on what your weed densities are. But it also creates some opportunities. So potentially you can start using new herbicides. There's, I don't know whether they're rumours or it's fact, but herbicide company representatives tell me that yes, there are herbicides that are probably too expensive for whole field use, but you can use them in a site-specific application. And also something that I guess is appealing to us is we can start developing alternate weed control technology. So we can start looking at novel techniques, non-herbicidal, to specifically target weeds in crops once we've got weed recognition. And we're talking about accurate weed recognition too. All right, so we're going to start off with a bit of terminology. This is something that we've had many discussions about, and even in the literature you can see that there's a, quite often inconsistent use of the terms. And so one of the challenges for us as researchers is that we have to try and come up with some sort of standards of what the terms are that we need to be using and that the industry needs to be adopting. All right, so weed detection, that's something that is quite common now. That's essentially what happens in fallow. So you're detecting a weed in an area where you're not particularly concerned about what else is around because that whatever is green there is a weed. For weed recognition, we're talking about identifying or recognising a weed in a cropping system. So you're specifically differentiating between the crop and the weed. So you're recognising if that's a weed and that's not. Okay, so that's...
So not at a species level, just crop level?
Not at, well, that is, yeah, that's right. But when we get to this level, so this is weed identification, this is where we're talking about the species level of whether that's a turnip weed or a wild radish weed or a ryegrass weed or whatever. So again, you've still got the differentiation between crops and weeds, but you've got more resolution to identify what that weed is. Okay? Yep. Good. So today, well, for the next couple of days, we're really going to be focusing on this weed recognition side of things. But we do touch on this. So just keep in mind these terminologies. You happy with that, guy? Yep. All right, so developments in weed recognition technologies or camera technologies. So this is not sensors now, we're talking about cameras. So the current site-specific spraying technologies are pretty much based on sensors, so weeders and weed seekers. The future is very much about cameras because they can obviously do a lot more than sensors. And there's lots of them, and that indicates quite clearly that there's a lot of interest in weed recognition in general, not just in grain production systems, but in all of agriculture. Lots of interest and lots of development. There's lots of development going on in terms of algorithms. So you've got to have the camera, yes, you've got the images, but then you've got to have the software behind that to actually identify what's in those images. And there's lots and lots of equations, if you like, being developed to help people recognise, identify weeds in those images. Again, demonstrating that there's a lot of interest in this area. And then we've got all sorts of different weed control capable platforms being developed all over the world, mostly in Europe, I would imagine. Fair comment, probably in the US as well. So these are all platforms that mostly autonomous, developed for weed recognition and potentially control. So again, demonstrating the global interest in this area. So lots of stuff going on. There's a little bit happening in Australia, but I don't know that we've really looked carefully at what the technology opportunity is in Australia. And to do that, I think we have to actually start by focusing first on the cropping system and then figuring out what we actually need of all this technology development to help us recognise and control weeds site-specifically in cropping systems. So we've had a little bit of a go at that, and we've started off looking at the weed control opportunities, and we've come up with two general periods for weed control, if you like. And they sort of fit with the way that weeds are currently being controlled in that cropping system. So the first period is the early post-emergence phase, and that's obviously the critical one. That's when weeds do the most damage to yield potentials, so that's when we want them out of your cropping system. The second general period is that late post-emergence phase. So there, the opportunity has passed to prevent yield loss. It's more about preventing seed production and subsequent problems in your cropping program. So you're trying to target the weeds before they have a chance to produce viable seeds that go into the seed bank. So I guess it's a bit like mopping up the survivors. So what are the weed control scenarios during those respective phases? So early post-emergence phase, you're going to have a range of weed densities potentially. In Australian grain production systems, you've got a large area that you're going to want to control weeds across. You've got a fairly short time frame, maybe 3 to 4 weeks. Open crop canopy, so the weed target should be readily visible. The weeds are going to be small. So in terms of the time frame, looking at targeting weeds at 6 hectares per hour to cover that 3,000 hectares in a 3-year period. So it's got to be something that's done quickly. And so what we think is going to be the best system for that is based on current technology. So a boom with cameras that can obviously operate reasonably quickly. And I guess the ideal opportunity there is something that's got combined blanket and spot spraying technologies. And I guess that's where GRDC have been focusing their efforts. So cameras mounted on the booms, and then those cameras are recognising weeds and then triggering the required nozzles to selectively control the weeds in the crop. And certainly that's where the focus of their development has been for wild radish and weed production systems. That sort of making sense? Yeah.
Benchmark what we've got for reflecting from our manufacturers as well, like John Deere platform to do that type of
yeah, look, it's an interesting one. I think, I mean, obviously it's focusing on fallow at the moment, but the cameras can be trained, and I'd have to think that that's what they're looking at for the future with this approach. I mean, it's interesting that this has been released in Australia. Well, it's great, really good, and I suspect that they're watching what's happening here and thinking, okay, we can start off with this and we'll transition.
Michael, is that talking about dual tank, dual chemistry, and dual line separate?
Yeah, well, I mean, again, this is my thinking. That's the opportunity that we probably want to focus here and target now.
Michael,
I could be wrong.
You
real capability is probably about half of that in reality, but just on field efficiencies of machinery.
Half the,
Well, I know we sprayed 23 kilometres an hour.
Oh,
and
okay.
we managed to do about 45 hectares an hour on average.
okay.
So it's,
I mean, it depends on boom.
it does, but it's surprising how slow you go, how much less efficient you become.
Yeah, okay.
In speed.
Yep. Yep. Good point. Okay. So the late post-emergence phase, the scenario now is that you should have low weed densities. Hopefully you've got on top of them in the early post-emergence phase. Still got the same area to control weeds on. You've got much longer window of opportunity here because it's just a mopping up exercise. More than likely you've got a closed crop canopy, so the ability to recognise your target is going to be a little bit difficult. And you'll have a range of weed sizes from small to large, depending on when the subsequent cohort emergence has occurred. So given that longer time frame, your required rate of operation, speed of operation is much lower, potentially. And that's where we think that maybe there's a fit for the autonomous platforms that are slowly moving through the paddocks. In this particular case, we had a little experiment looking at using a shroud that contained both camera and weed control technology inside it. In this case, it's just a demonstration type thing, so it's just operating in one row. So we have cameras collecting images, we've got the recognition process going on, so we're detecting, recognising the weeds within the crop. And I think I can play that somewhere here. So that's just a little bit of graphics of what it looks like. No, I can't speed it up. I'll skip the camera. Go back slide. No, back to start. Right. That's right. Yeah, and so through that project, which was again about developing an autonomous platform for site-specific weed detection and recognition and control, we looked at ryegrass and turnipweed in wheats and chickpeas, and we came up with some levels of precision in terms of being able to accurately recognise those weeds in those crops. They're not fantastic. They're probably not what, as researchers, you want. We were hoping to get to 95+% accuracy, but they're still, I guess, reasonable. And it's probably a question for the industry too, is just what level of precision is required for this technology. I mean, maybe we don't need to get to 95 before we can start commercialising the systems. Maybe a lower level of recognition is suitable. Obviously, it was more difficult to identify ryegrass. Ryegrass is really tough to try and discriminate between any crops, particularly wheat. So that was a challenge, but we did learn that it's a really laborious task to go through this process of looking at weed images and then trying to, on a pixel-wise basis, identify ryegrass in a wheat or ryegrass in a chickpea crop. So that's a really tough thing to do, is to get that annotation process right. And Guy will talk about that. Okay, so in terms of the weed recognition, how did that happen?
I might have reached recording.
All right, so now getting on to our project that we've talked about today. So this was the structure of the project. So we had a team working on the weed recognition side of things, and we've had a team working on development of open source database. And there's been quite a bit of interaction between the teams just to make sure that the images that have been collected can be stored suitably in the database and vice versa. So that's generally been the structure of the project. Essentially, it was a 12-month project, and we'll hear over the next, well, today, we'll hear about the accuracy of the weed recognition algorithms that have been developed, and we'll get to see the Weed ID database that's now openly available to the general public.
Yeah.
Weed AI. Yeah. Sorry. Okay, so go to the program. Yeah. Have we got any questions on all that? Background of where we've been and where we're up to? Okay, so this is the program for today. So next up, Guy is going to be talking about the weed image collection side of things. And then Asher will talk about the development of the weed recognition software algorithms. And I'll give a little bit of background about why we have gone down the path of an open source image database. Henry will turn up at some stage later this morning to talk in place of Joel about the Weed AI platform. And then after lunch, we're heading off for a couple of farm visits. We're always keen to get out on the farms just to help us researchers keep in context of what we're really trying to achieve. And then tonight, here it says, we've got a commercial hotel in Junee for dinner where apparently it's $5 steak night tonight. Right, I'll hand over to Guy. So we're a bit ahead of time.
Yeah, so I'll be talking about collecting and annotating images for weed recognition. Sounds pretty dry, and the process usually is, but I'll keep it interactive and a bit more fun. And as for those who don't know me, my name's Guy. Precision weed control scientist for about another month, I think. Then also part-time, kind of full-time PhD student in ryegrass section. So first up, I thought I'd start off with a video or an image here. And ask the audience and also those online as well what they would make of the content in the image. So if there's a agronomist, Greg, if you saw that, what would you say within the image from an agronomist's perspective about perhaps weed control? Any ideas?
Yeah, then some fellow with a single or flea bane.
Yeah, so that's what I was keep a flea bane. You've got potentially some sort of cereal stuff there. Looks pretty fresh. Also some fallow, so in 10 seconds we're able to give you a species level understanding of what's in that paddock, as well as paddock history potentially, and I'm sure you've already got control options in mind about what you apply to that, right? So that's how good humans are. Well, Greg's pretty good too. But as a whole, we can make derive a lot of understanding from him really, really quickly. So we can look at a room, we can count people and like that, we can understand emotions at the same time as talking and try to think about what to say next. We're just very good at doing lots of things. And they're trying to get computers to do that. If we ask the computer what it thought it was, if you contain grass, outdoor sky and field, right? That's not going to be much help, much use in a farming setting. So that's what just PowerPoint told me it was. Like again, if you went to an image, I could probably outline the there and you get a better understanding of how many or what density there was with almost no awareness of where that is or having seen that before. And so I guess that sets the bar pretty high for computers because training humans is a lengthy process. And we learn through theory, experience, and going through books, field visits, field walks, looking at new things, charts, research, all that sort of stuff helps us. I'm not going to try and explain learning theory because that's well beyond what I do. But just to give you an idea of the comparison and how we need to, in the future, start training computers. While we might perform and learn in that way, computers learn to see very differently. And so we're specifically focusing on seeing, so visual awareness or understanding of things, of our surroundings, and less so on things like sonar or LiDAR, those sorts of data forms. But at the end of the day, a computer just gets numbers. Unfortunately, it's fairly bland. So this is an image over a ginger leaf. And what you can see behind there, if I zoom in a little bit, sense of pixel level intensities. So when we look at an image, we just see an image. I apologize, some people here might already be well aware of this, but I thought I'd just set the baseline, and that sort of defines then how we collect images and go through a data annotation process. But anyway, this is what computers see, and we're going to relate that to a weed somehow, so it can do this. And that's quite difficult, I guess, because that's how computers work, but we want to translate that to a visual and some sort of output and action in particular. And that's the domain we're operating in, so that's what we're trying to do. If we want to get green on green, we need to have enough data and enough examples of this sort of information, which are images at the end of the day, to be able to do this. And I guess to explain a little bit more about these numbers. So behind every image, you have RGB image, so red, green, and blue. You have three different layers of pixels. You've got red, green, and blue channels, and each channel typically has an intensity from 0 to 255. So this green area might be 255 in the green, and maybe very low everywhere else. And so these dark areas have generally lower intensity levels because they're darker, whereas 255 is the higher. So anyway, that's just a bit of background about how computers see and how we need to think about how they're going to work in the field, I guess, and understand it from that perspective. So obviously the weed control, what we're trying to do, and Michael's talked a little bit about this, is the weed control defines our approach for data collection and annotation and all that. So the first thing is to work out, well, what are we doing? We're doing lasers. What's the level of detection accuracy do we need? Are we doing in-field spot spraying? So like you see up here with the ryegrass system, or we're doing sort of inter-row weeding that Michael talked about, or even targeted utility spots. Each of these options have a slightly different level of detection and precision that's required with it. And once we decide on the recognition approach and what that entails, things like speed, how much precision, so do we need that level of precision enough, or we need some millimeters, and the control mechanism, and that helps us to define our data collection standards. So we collect data in this format, what really helps us in this format, and also then the annotation, because the annotation of the architecture or the precision it gives us, I'll talk about later, like the more useful here and so there. And then, of course, the computers, the amount of processing power as well, and the cameras and all that sort of thing used. So that's the background behind it. And so now we'll move to the first step of the weed recognition methods. So once we understand the weed recognition methods that Michael showed briefly, then we can go through our data collection and annotation process. So the first one in that, and each of these has an increasing level of precision. So in the field, I guess, definition of that. So it's how precise or how close to your desired point of control can you get. So the first one is what's called image classification. And so this is sort of what we saw in that very first image of the fleet name in that colour field. That's PowerPoint just gave us this broad classification of what was in the image, right? There's nothing on location or anything else. And so what this would give us is just that turnipweed is present. So some here, we've given enough data with turnipweed present and turnipweed absent that it can now tell us that, all right, this image does have turnipweed. Again, it's quite coarse. It's restricted to the field of view of the camera, and might be good for spot spraying or weed mapping, those sorts of things. But trying to target a laser in here could be difficult. There are some methods of mapping the contribution of each of those pixels to that classification outcome, which people can use. So I won't sort of go into that, but broadly that's they're quite coarse, I guess, in terms of how granular it is. Then we get the bounding box or object detection. So now we're getting much more information on the number of weeds in the image and also the location of them. So this is more precise. Then we could use the spot spraying or targeted application of herbicides, those sorts of things. But the annotation process that I'll go into later is going to actually draw boxes around these to tell it where and what they are. But we know there are 4 turnipweeds, and we can potentially say the center of the box might be the center of the weed, but we might not be very confident in that. Then we have, this is the segmentation. There we go. This is semantic segmentation. So now we're at the pixel level. So like I was talking before about each image is made up of 3 layers of different pixel sizes. So each of those numbers is a pixel. And now we're getting down to the defining each of those pixels and assigning it to a certain class of weed or whatever you're detecting. And so here we've got all the weed groups. So now you know there are turnipweed pixels and nothing or other pixels. And so it's more precise, I guess, but you also lost a little bit of information on individual plants. You don't know there's 4 turnipweed. You just know that there are this many pixels of turnipweed. So potentially you could target these with like a scanning laser, or there are more targeted methods. You don't have that box, so you're not hitting the background. But yeah, then we've got instance segmentation, which sort of combines that object detections. You've got the number of weeds and also the pixel level. So this is the highest level of information you could get at the moment if you're going for these sorts of detectional approaches for recognizing weed. You can do other things like key point detection, or you could change, you don't have to segment the whole leaf, maybe you can segment out individual leaves, you get leaf detection. You can adjust this to your approach, but in terms of the level of precision you can get at the moment, this is about. And that's highly targeted methods, because I mentioned you could actually outline and train your model to detect growing points or leaves or that sort of thing. And that's probably, for the lazy, potentially the lasers or very targeted herbicide jets.
Before you move on, Guy, is everybody comfortable with the different levels of weed recognition and the types of weed control that you can potentially use for those?
I'd say once you get beyond classification, you use these, some like I've sort of put them out, I guess, as very strict classes, but there are ways of getting around, like even your model might give you this, but it's clear that these 2 plants are separate. So that could give you a form of instance segmentation from a semantic segmentation model. So there's like, well, put them up here as very distinct classes, there is a little bit of grey area.
So in terms of one on the top left, so a selective herbicide would be the option that you know that there's a weed there. You don't know where it is, so potentially you would trigger a selective herbicide.
Whereas these ones might go down towards non-selectives in crop. Or
yeah, so you know where the weed is, so you potentially target with a non-selective herbicide or not. If you're not, so you're not being able to discriminate exactly the area of the weed.
You got better section boxes out. This is obviously separate crop. If it was a larger crop, that'd be part of your weed plant. You'd be spraying that as well.
A bit of a course of weed control, whereas in the bottom left, you can be quite precise about how you. I mean, you might have a focused nozzle that just works specifically on that leaf, doesn't get around it. And then, as I was saying, on the right, you can start in targeting specific parts of the plant, like the growing point, the flowers, that information.
Is it reflected in processing capacity as well?
Yeah.
Yep. So these models are much faster, and these sorts of models actually use a classification model often as a backbone to it. So it forms a classification, and there are other parts of it that then do the pixel-wise. So these are slower frame rates.
Based on Mike's description of what you're trying to achieve, sort of directs the approach you're using.
Yeah, exactly.
I'm not sure if I was going to get into the next couple of slides, but also corresponding this is as you increase the complexity going in time, it's to increase. So it becomes harder and harder to do instance segmentation, for instance, because the operators have more information and training.
Do we have the mechanical needs at the moment to implement that instant segmentation from a spraying point of view, or that's?
So machine learning is a bit of a misnomer. It's actually a lot of human mediated human teacher. Yeah. As Guy will demonstrate.
But yeah, you can think up ways of having very, like the original Blue River, but they moved away from that. But you have very selective jets or something. That's why.
You detect it and you can do something to it.
Yeah. So, yeah, basically the idea is once you know where it is, then you can do something about it. And usually doing something about it, or designing something to do something about it is a bit easier, but actually making sure it's effective is also difficult.
So, and I should perhaps wrong, you're saying that instant segmentation.
Yep.
It could not just be the 2 individual weeds, but you could actually have the growing point being a different colour if that's your target.
Yeah, so I mean, this example, this isn't actually a model, I've just done this by hand, but if you were training a model, you could label leaves separately to say flowering points or like a flower or growing points, or if you have a defined area you want to target, you just label that separately to just whatever you call. Yeah, you can be as fine-tuned as you like.
Because we understand any tool you want to use in the segmentation before.
Yeah, so you have to work out what you want to do first, and then what level is needed here. Because there's trade-offs, as I said, with speed, and as Ashley mentioned, with labeling time, which
And so a point with all this is that you have to be aware of what sort of weed control technologies are available to use. So, you know, we've been playing around with a little bit of lasers, so you can't use lasers unless you've got something like that implementation and by the growing ones.
Can you give me a rough idea of the latency, relative latency increase that is how much longer it is? What's the frame rate?
I should plug it a little here, but I've heard like around 8 frames a second around here. Is that?
Yeah, well, I can tell you semantic segmentation. You know, one of the previous projects we were doing something like 10 frames. With object detection these days, you can get up to 160 frames.
That's on a code on the road.
They're running the same, effectively. We're running this.
But yeah, it does, as Ashley alludes to, it does depend on what sort of graphics card you've got.
Yeah.
Like the latest NVIDIA stuff that costs $2,000, you've got to run these pretty quick. But then you have little better computers or it changes things. So it's a bit variable, but it sounds good.
I did have a PhD student who was doing instant segmentation in horticulture. This was a few years ago. He was getting like a couple of frames. So quite a lot. And obviously, if you've got big farms like and you want to travel fast, then you need to transfer, right? So that's a good framework.
I'll keep, no one's happy with that. I'll just keep going on. So once we've got the recognition method, then we, as we mentioned, talked about a little bit, we can work out how we collect image data and answering why, like what's your problem, why are you doing it, is a good place to start. And this was a quote from a John Deere guy at a Zoom conference in San Francisco. So basically, do you collect 1 million images from one field or 1 image each from 1 million fields? And so it's, in the machine learning community, it's probably quite clear what the answer to that is, because you want diversity if you're trying to cover a diverse range of paddocks. But perhaps you are just trying to treat this amount of area. And if you know that area really well with your data set, then you might be better off doing the former. But in the agriculture perspective, I think, or most perspectives, or most fields, it's probably better to do this latter one. And also things like data gaps. So if you have a particular weed species or particular growing environments or background conditions that you're trying to fill the gap with your data that you might have low performance on. So then also the weed control method. So obviously this sort of data collection method in Ginger isn't going to be very relevant for inter-row cropping and weed. And then that helps work out how you're going to collect data. So the technology, as I said here, so the cameras and processing, or image sizes, the collection parameters, so how you collect this, speed, angle, those sorts of things, color, lighting, artificial lighting or not, and also matching your data collection for the use case. So if you can collect image data from anything, like your phone, any sort of cheap camera, but if you're trying to develop a production level system, then what you really want to do is collect it with that system, because it reduces that variability. You've got enough variability in the field, you know, the variability in your collection and your cameras and that as well. So you've got to try and match that as best possible. But the starting point is always good to get just some data, right? to get you going. And once established, I'd probably add that collecting image data is probably the easy part once you've got that system going, because you can collect thousands and thousands and hundreds of thousands, millions of images as you go along. And that's what I imagine all the camera-based booms are doing as they drive over fields. So once you've got the system going, collecting data is the easy part. But getting the diversity and the relevant data is more difficult to make sure you actually get useful weed images in a variety of growth stages. So there's always the question about phones. So do phones work? And as I mentioned before, they're a good starting point. It's a chicken and egg thing. Like you want to make a model to detect weeds, but you don't have any images to detect them with. So you may as well go through the phone. Or if you don't have the platform to detect them on, so where you start, well, the phone could work. And Weed AI, as we've got into it, does sort of support that as an initial starting point. Because it's very low barrier, and farmers and agronomists are out there already on their phones onto it. So, but once you've collected the images, you end up with this. And now you're trying to make head and tail with it. Because it's a lot of wheat and it looks very different on a 2D plane than it does on when you're actually standing there looking at it. And I've brought up 2Ds. 3D is another option for collecting data. The stereo cameras, another camera feature. We'll stick with 2D at the moment. Anyway, that's what it looks like at the end. So just going quickly back to what the computers see, because the whole point of this is to try and get as many examples of a pattern, the weed, the set of numbers, that it learns in that set of numbers, but where the pattern is and what it is, to differentiate that pattern from the other patterns in the images. So just to bring it back to that, now we'll go to the annotation side of things. So this is me up in Narrabri annotating the images. And it takes a long time, it's super tedious, as you can tell, because you sit there and you just draw boxes around ryegrass for endpoints. And you can do that for days and days.
I think it's not can do it, you need to do it.
Yeah, you have to, right? So if you want to detect weeds in your crop and you want to realise the benefits and the huge benefits of site-specific weed control, this is the unfortunate reality. And that's sped up 10 times as well.
Guy, what's the level of difference between those raw numbers that you see across the ryegrass? Like, are you seeing a big difference even in those numbers just across one species, or are they pretty consistent? That's pretty the bare bones stuff. So you always get derived information. So you look at things like edges or flavour, shape, and colour. So I haven't looked specifically at ryegrass to other species. There's some papers that have looked at it. I think there are some spectral differences between, say, ryegrass and wheat. But that's opposite. So spectral means colour, and if you have a nutrient-stressed wheat or a nutrient-stressed ryegrass, the colour changes. So often, while I show the numbers there, it's the relationship between numbers next to each other as well that might define an edge of a plant, and then a combination of edges then defines the shape of the plant that is potentially more indicative. And these days, all the deep learning models that we're mostly referring to, they automatically extract all those features in the shape and colour texture order for you, so you don't have to go through and tell it what to extract. So, there are options of doing a little bit of everything, so you can tell it slightly what to take out and direct it, but at the moment it's pretty automatic.
Is that also the quality of the cameras that you go with a hyperspectral camera that assist in that differentiation, or is it still looking at the same things in the broader line?
I guess if you went down the hyperspectral route, then you're hoping that there's a difference in the spectral. Yeah. So you're probably changing more towards, or you're trying to understand spectral differences as opposed to shape and structure, which the other convolutional networks probably try and do. It's a little bit beyond what I do, but I should that early.
My impression of that is the sort of noise making that you get. So there is a difference in greens. They're asking the ryegrass stuff with people more.
Mine's more was a statistical difference, or was it raw numbers of the camera that were driving that recognition?
So, I mean, we did see statistical differences in CPS, and if you look at a hyperspectral image, you see that it's spread over more panels. The problem is there is a little statistical difference, but there's also a big spread, so they can't overlap. And if you're operating in daylight, depending on how the data is changing, then you don't really have an absolute reference of the unit. So it becomes quite tricky. So I like spectral data. I think you can do interesting things with it, but it does not.
So I think the general consensus now that we're moving more towards just focusing on digital cameras rather than for a range of reasons. Cost is one of them.
Also, you have so much data with a hyperspectral camera. Like you think that, so with a normal camera, you have 3 channels, whereas a hyperspectral channel, the camera you might have thousands. So you end up with what's called a data cube. You've got layers. So it's unwieldy, I guess, to the process.
So the other slight nuance to add is there's hyperspectral and multispectral. So technology is reaching a point of multispectral cameras where you get a 2D image. So you see a plant and not the image. But with hyperspectral, they're still mostly scanned. So it's actually a one-dimensional image, where one dimension is spectral and the other is all the spectral bands. So unless you compile it, which are different together, a human operator can recognize what's in that image. So it is difficult.
But so after that annotation process, end up with stuff like this. This is like just the weed AI logo all the time, but end up with thousands. I think in our models we had like 12,000 plus instances of ryegrass, turnipweed, and southwest, which is what's present here. So yeah, this is what you're dealing with, I guess. This is what you're telling the computer to see, and then within each of these boxes, you have those numbers, right, that you're trying to detect patterns in. And so that, if you give it enough examples, if that difference, if that signal is really subtle, you can start to get pattern emerge. But yeah, that's what the output is. Then, as Ash was talking about, the laborious process of segmentation labeling, so semantic segmentation and instant segmentation, effectively the same labeling process. Just depends how you label each instance. Instance is a little bit more difficult because you have to identify individual weeds and bulk plants and then outline leaves, but if they're overlapping, this is a ginger plant. Yeah, very tedious because you have to go and outline every single part, because you want a pixel level output, you have to input pixel level annotation.
How much longer do you reckon it takes them?
So these images were roughly 1 to 2 hours each. That's probably fast. And yeah, each of those bounding boxes, depending on what crop it is, you're looking at maybe. I think the average across our group is like a minute per image. You see, these are small south. I think that's big weight actually.
How do you select the green channel there and just build the edge finding, run an edge finding?
Next one. Shocking. And anyway, so this is what the output is. So you can extract the individual plants out of it. And yeah, that's what you end up with. But as Eric alluded to, you can be a bit smarter about it. It's a bit of a chicken and egg thing again. You don't want to just select anything that's green and then exclude any dead or dying parts of the plant that you might want to detect. Or if you just detect green, then you can use the green algorithm to detect the crop. But if you do have well-spaced weeds, you can start to develop your own extraction programs like this one to put together. So just basically extract weeds based on green, like I said, using XG. Index, sorry. And so this is what we call, I guess, assisted annotation. So this is color-based, so you're just using XG, an algorithm that uses green, but you can also use thresholding on different color channels or a range of different options. But if you want to be more smart about it again, you can say get 100 images that take 2 hours each or an hour each, and they'll train a model on that. And then you run that model on the rest of your images, and then you edit those images that's labeled, and you can start to understand where it's falling down a little bit, where it's got low confidence, and that can improve it. So getting that first 100 or first few images done is the difficult part, but then as you do more and more and more, it opens up more doors to use more assisted or unsupervised methods.
So related to that, Arnold's given us a question on Zoom.
Yep.
He says, after having collected and annotated many images already, what is your impression of the database size, I guess, to be able to use this sort of...
to run model assisted?
Yeah. So what's the sort of baseline and how reliable do you see that being?
Hard to give you a full figure, Arnold, but it's probably, it depends, it's a depends question, because it's about the diversity of your data set, how many classes, or how difficult it is to detect that weed in crops. So say for ryegrass might be different to turnipweed, because turnipweed is so different to wheat. So it does depend. With our work on some of this ginger stuff, we've been doing right with around 100 images to get a somewhat decent output from the model that you could potentially then use to correct. That was for ginger, which is probably a slightly easier option because you've got very clear plants and not as much overlapping. But yeah, you want at least probably 1,000 or so images before you start bounding boxes. The more the better.
Joel has just commented on that now.
Oh, yeah.
Doing some learning curve analysis on different kinds of data set would be interesting.
Yeah, there's really interesting tools you can do to work out sort of targeted annotation. So where's your where are your weak points in your model? So where's the low confidence detections? And if there are low confidence detections, then targeting your data collection. So it's always a feed-forward process to those low confidence things. And again, there was a really good presentation by John Deere, head of technology, last year at that same conference that I took that quote from, that talked about the way they've analysed their data sets and their outputs and how that then feeds into where they collect and how they annotate that data. So there's a lot more intelligent things you can do than just green. But it does take a fair bit of engineering to do that. So some of the other options for improvement, to quickly mention, is data augmentation. So because you can extract all those weeds and images from the background, if you're doing a segmentation method, or the extraction of green, you can then actually start to develop synthetic images. So here is a backdrop we're taken on a row bed, and we just pasted ginger and weeds in a random fashion onto that. So then you can end up with this artificial image that is random, so it doesn't learn any structure or you've given it. And also you can set the number of weeds or that sort of thing. So you can improve your data set that way. And Caleb will talk a bit more about this tomorrow. But what we've seen is synthetic data performs almost as well as field data only, because you can quickly generate thousands and thousands of iterations of this with like the click of a button and then have to label things. But it won't necessarily perform as well because you don't have the right backgrounds or the right training data set. The other option is to do geometric or photometric changes. So this is where you might flip images, crop them, zoom in, just change how the plant looks to the model. And data augmentation is a fairly standard process to improve the accuracy and reliability of that. So it starts off looking really hard, still is hard, but there are some options to make it a little bit better. And so in summary, I guess it's annotation, as we've seen, is very, very tedious. It's definitely a bottleneck at the moment. And while there are some ways of alleviating some of that pain, it's by no means an easy way out. You do have to spend time labeling and do high quality labels to get that high quality recognition algorithm that you want. If you have poor data going in, you're going to have poor data coming out, particularly if that signal or the difference between the weed and the crop or whatever you're trying to detect is very, very minimal. Because again, you're going back to the numbers. They don't understand anything about surroundings, just pure numbers, so you have to be very careful. There are some options for improvement that's been through, and importantly, we have to work out what weed control method we're using before we can define an approach, which then defines our data collection and then also our data annotation. And there is a lot of room for collaborative efforts, which is part of why this project is important. Yeah, thank you. Thanks for the interaction as well. Any questions? Any questions online?
No new questions online.
You really quickly sort of touched on the idea of 2D versus 3D, putting a 3D camera on a bit more, I'm hoping you I know that there is some very significant logic that is including, what could you comment on what benefit including three-dimensional data might be to improve differentiation?
I think there have been a few papers which shown it's been a substantial benefit, I guess, because as you mentioned, there are some morphological differences or height differences between the crop and the weed. And also understanding, say if you want to deliver some sort of weed control to that weed, it's good to understand how high or how far away from the camera or how it moves in the 3D space as well. You say like wire weed, it's very extensive on the ground, but things like fleabane are quite tall, and fleabane from an angle over here, if it's tall, you might try and hit the top of it if you don't understand that it's tall by having that 3D awareness of where it is. That's if you're trying to do something physical to it as opposed to just spraying at the top. So that, I guess, that side of it, the weed control side, and then I think having that extra, at the end of the day, the third dimension is just another data stream that's coming in, still as numbers to the computer. So you might have 3 layers. You have the red, green, and blue layer, and then on top of that you have the depth layer. And so when you annotate that image, you've got, I guess, 33% more information to learn from, and that layer might be really important because of what we mentioned before about type. So it's just all about giving it more information, but if you give it too much, then issue 2, I guess, it's too slow. And also, if you're processing 4 streams of information instead of 3, you might have more difficulty with the speed. And there's always trade-offs.
So I think Joel had a question online.
You want to add anything else, Joel?
Oh, just very briefly, I suppose another issue there is just technology as you talked about. So you can do stereo, that's kind of what we're there are red, green, and blue depth numbers, which is what the next book's about, but they work out against the environment. The strain in the sun, there's an awful lot of infrared, so they tend to fall over. So there could be benefit, but at the moment I'm less uncomfortable in all this technology. 5 years.
So I'll comment on 3D or
I'm not sure. Joel, did you want to ask your question? If you have one. You may have just unmuted himself.
I just want to give a quick comment on 3D. And it's in relation to keeping in perspective of what else is going on in this area. So cameras are going to be used for other things besides weed recognition, and there's a lot of interest in using 3D cameras for measuring crop height and other things. So we have to keep in mind as we move down this track that there's other technologies that come along. So rather than move the way.
Some birds that have a camera on in their eye already.
I'd say one of the major benefits of cameras is that while we've been talking about algorithms for weed recognition, you could equally have one for nutrient deficiency or insect detection too. So cameras, because it's all just data against numbers, you just tell it what to look for and it'll hopefully look for that with some level of accuracy.
Guy, I think your second dot point on that summary slide about weed, third one, weed control defines a recognition approach. Yeah, I get that. But what about looking forward in the future?
So, as in novel, the recognition approach.
Yeah, things that we don't know. So you're limiting future options.
I guess I would.
Control options.
Yeah.
Yeah, I guess it's probably two streams of thinking.
I think it has to be parallel.
Yeah. So you can do like lasers are pretty sort of wild, but yeah, at the same time you've got an opportunity for that level of recognition happening. So it's probably that was more in the mindset of someone who's developing, say, a product or something to put to the market. That if your company or your product is spraying, then your recognition approach is probably going to be this group over here.
I think, yeah, as Mike said, you can do a parallel, and it's probably important to do a parallel. And importantly, it's always good to keep in mind what you're trying to do, not try and solve problems that don't exist.
I think it's also possible that some people reasons for the technology and also the category of actions. So if you're doing pre-emergent spraying, that might be a different type of application regime to doing inter-row weeding and non-quantitative or machine vision approach. Each of those, so the technology delivery can still be but just the application domain sort of
I think one way of thinking about it is in terms of cost. So the reason why we do play around with lasers is it's a really low cost opportunity because if you're just targeting the growing point, then that's going to be really cheap to build. So anything that can just focus on that growing point is probably cheaper to build. So if you can start focusing in on maximum reduction in cost. Exactly.
I was going to bring my computer over there so that people use it on Zoom can participate as well. Doesn't work.
Right. Everybody happy with that? Just a final comment on all that, just in case we missed the point, that the more complexity, the more annotation you're going to need, and you have to think about your weed control scenario to try and reduce the amount of annotation. So if you're just going to focus on, say, wild radishes, really grass stage of wheat, then wild radish in crops in general, then you're going to need every growth stage of wild radish and every growth stage of every crop. All of Australian grain crops. Not just the crops, the weeds, the background, environment, etc.
How much of the electricity is that annotation gap? Or you not quite there, or the annotation hasn't annotated the spectrum that you're experiencing, or is there a feel for where that gap is coming from? That would be something out of that pattern. Lots of these architectures are designed for built environments, so that the model, like the architecture is how to target the algorithms together. When you train algorithms, you're just like adjusting into the way. And so these architecture designs build vegetation at one plants or trees. And what we're trying to do is change that to differentiate between vegetation types and within similar sort of species, or even like very subtle differences. So I think that's where the difference comes in. And like my theory is that if you need more, if that subtlety is like very subtle or the difference is very small, and you need more data to try and develop an understanding of that pattern. So the 80% comes from that inability to recognize that pattern well because it's quite simple. That makes sense.
So we've had a question. Vicky Green from Toowoomba asks.
So Vicky asks, I'm wondering how much role there is for standalone weed mapping versus recognition associated with a simultaneous control action.
Okay. So yeah, this is a perennial question, well, not perennial, but it's a constant question at the moment. So is there a role for, say, weed mapping with a drone initially in fallows or potentially in crops to identify the weed targets for subsequent spraying? I guess there is, but our feeling has been that we need to be have this proximity to target approach where we're angling for, pushing for the mapping and control all to be in one process. And the reasons why we have gone down that approach is that There are issues with using drones, particularly in large grain production systems. In fallows, you can use them to identify the weeds for subsequent spraying with boom. It doesn't have to have really good section control, but it can be done. We just believe that there are weather-related issues that are going to really restrict that feasibility across large-scale production systems. If you only had a couple of hectares, I think that would be fine. It's quite easily doable. But in large-scale production systems, I think it's inherently difficult to do it properly. Anyone else want to?
Well, I think there are a lot of challenges. Probably one of the giants that has been trialling it, and even from a perspective of getting that into a controller has been difficult under file sizes and just different manufacturers and how they control the different. So the case screen that controls the rate control width. It's just good. Just have no idea. So straight systems are quite simple, but yeah, I think from even and then there's the RTK reference point as well, which we're aware of.
Okay, so we're going to go through the process of repeating comments, questions to make sure that the online audience.
Yeah, we are planning on putting a phone onto the table as well, so that we can have interaction between our online audience as well.
But just to repeat that comment, the feedback was that there's some software incompatibility challenges, some technology issues that are making that not such a simple, straightforward process to match up drone collected data with a broom spray delivery. All right, so now I'd like to introduce Asher Bender, who's going to talk about the development of recognition algorithms. So Asher works with the Australian Centre for Field Robotics, based in engineering, and yeah, we've been collaborating with Asher for a number of years now on these technologies.
Great, three, four.
Yeah.
All right. Thanks, Michael, and thank you, everyone. So yeah, in the talk, I'll cover some background in object detection and how they're implemented. Then I'll be covering how we measure the performance of these algorithms. It will be a little bit technical and lengthy, but I think it would be nice if you guys could at least walk away with some understanding about how to rank and measure the performance of these things. And then I'll show you some applied work we did with data that I collected in wheat and chickpea crop. So we've been through this a couple of times this morning. What is object detection? The basic process is we want to take an input image like this and have some process or algorithm output bounding box detection. So determine the location of objects that we're interested in and also provide a label describing what these objects are. So how did the computer vision community tackle these sorts of problems in the past? So Guy alluded to this. The early approach was feature engineering. So up until neural networks became popular and easy to deploy in around 2010, the community spent a large amount of time looking at various types of image features that they could plug in to classification algorithms. Some of these are very simple. They kind of do what they say on the box. So you've got things like edge detectors. They pick up edges in images. Same with corner detectors. You can see it's localizing the corners of windows and doors. Feature descriptors are a lot more abstract. They're hard to give a human intuition for. But what they tend to do is find salient points in the image that have certain properties. They might be scale invariance, might be rotation invariance. So, like I said, the way this used to work is, say you wanted to detect weeds, you'd choose a bunch of these filters, maybe there'd be some other texture, maybe there'd be some shape, and you'd push them into something like a support vector machine, so a classification algorithm. The reason why this doesn't really work is what happens if you now want to look at a different weed. So we've just done turnip weeds. What about ryegrass? The problem is you have to now re-engineer all the features. And that can be quite a lengthy and painstaking process. So it's not very generalizable. And results sort of languished up until deep learning started taking over. So you can frame object detection as a supervised learning problem. So we give some algorithm F input images and we want it to output detections. Instead of going through this feature engineering approach that we've just talked of, a nice way to do it is to learn this functional mapping. And this is what deep learning in neural networks has started to offer us. Some theory shows that if you have a neural network with only one hidden layer, but a layer that is arbitrarily wide, you can approximate any function. So it's a universal function approximator. If you look back to the way we can frame image detection for some sort of mapping or function, you can see how that's useful. The neural network can start to learn that mapping. In practice, the community's found that shallow networks with very wide layers are actually quite difficult to train. So in practice, what you see is networks with more layers, so deeper networks with narrower layers. And that makes up the majority of effective algorithms out there. But the thing I think I want you to take away from this is that neural networks, they're a form of function approximation. And the cool thing about that is it's automatic feature extraction. So deep learning gets thrown about a lot in the media as sort of the next best thing. And it's pretty cool, it's effective. But really, in terms of image processing, the thing that's going on that's contributed to a lot of the major leaps forward is this automatic feature extraction. Now we've defined a process of how to design object detectors rather than having to define the features, which was time consuming and expensive. To swap the task, we just need to swap the data. So, a brief overview of how these modern algorithms work. So, very obvious, starting on the left, we input our images. They go through what's colloquially called a backbone. And this is exactly what I've just been talking about, sort of where the magic happens. It's a large part of the network that decomposes the images into a bunch of features. It would be nice to say that we can learn something from these features. What does it mean to describe a turnip weed? But in reality, these only really make sense to a classifier. You can abstract them a little bit, but most of them don't have an immediately intuitive explanation. Next along the pipeline is a small part of the network. It does a little bit of processing. So one example is it concatenates features from multiple scales in the backbone before pumping it further down the line to the head. So in the head of the network is where I suppose you could say the detection happens. There's two sort of hierarchies of algorithms. The older type, but still quite effective, are two-stage detectors. And they have this extra block that basically looks at the features and suggests regions for the classifier and bounding box regressor to find objects. The disadvantage of having this extra complexity is that these algorithms are slower. They're quite accurate, but they're slower than the one-stage detectors, which I'll talk about now. So with one-stage detectors, we do away with this region proposal part. Instead, we have a dense set of points, so densely predict where objects might exist in the scene. The nice thing about this is they're a simpler type of hierarchy, or architecture, I should say. And so we can get high frame rates of inference, like we mentioned before, up to 60 frames a second. They're also easier to train and have been, they've been having the leading results in benchmarking tests. So this isn't going to be too technical, but I thought I'd talk about how we measured performance. Intuitively, accuracy might be something we like to talk about. Everyone has a sort of an intuition for what it is, the proportion of correctly classified instances. If we're trying to classify weeds, you can say in a scenario of 10 objects, if we get 2 wrong, this weed was not detected. this wheat was detected as a weed, we're going to have 80% accuracy. Easy, nice to digest, but it starts to break down if you have a class imbalance. So you can imagine if you've got a very big field, you've been doing proper integrated weed management, you're not going to have that many weeds, or at least you should hope you don't have that many weeds. But then you get into a case where, say, you have a minority of weeds, there's going to be a big imbalance between weeds and non-weed area. So if you go to one end of the extreme and you're always detecting crop state or dirt or fallow, you're still going to have a very high accuracy, right? Because that's the majority of the environment. You'll never detect a weed, and so you'll get a minority of, I'll probably get this wrong, false negatives. If you go to the other side of the equation and you're always detecting weeds, at least you're never going to miss a weed, so that has utility, but you'll be getting a hell of a lot of false positives. Every time you see dirt or crop, the classifier is going to go bananas. So you can see how this is a bit problematic. So Guy alluded to this morning. There are other metrics we can use to kind of measure these qualities. So accuracy we have a feel for. There are these two others called precision and recall. The maths isn't too important. Basically what they measure is sort of an intuitive feel. Is precision somewhat measures the quality of your predictions, whereas recall somewhat measures the relevance. And the way this works in the previous example, if we take that classifier that's always detecting crop, so again, we've got that high accuracy, we've got a minority of false negatives. It's going to have a high precision because we're often right, but it's going to have a low recall because we're barely ever retrieving the objects that we're interested in. So we're never retrieving weeds. The opposite extreme, we're always detecting weeds, very low accuracy, overwhelming majority of false positives. It's going to have a low precision because of those false positives, but now it's got a high recall because we're always returning the weeds that we're interested in. So rather than looking at accuracy, you can see how we might want to say balance precision and recall. And you can see they're inversely related. When precision's high, recall is low, and vice versa. So one of our objectives in designing these detectors is to balance those two parameters. But object detection is not just about classes, right? It's not just about turnipweed, ryegrass, wheat. It's also about putting a bounding box in the image that localizes these objects. So we need a way to measure the performance in that regard. The way the community does this is using a measure called intersection over union. It's actually quite intuitive. Say we take a ground truth bounding box, so something that someone labeled, and a candidate bounding box that the algorithm has come up with. The IOU is the intersection of those two boxes divided by the union. You get this nice value between 0 and 1 that measures the fit of the boxes. So you can see here for an IOU of 0.4, it's quite a poor fit, ranging up to an excellent fit, which is 0.9 IOU. So it's a nice way of measuring similarity between boxes. So I've got three components now: precision, recall, and IOU. How do we combine them into one nice metric that we can rank these algorithms? That's called the mean average precision. It gets a little bit difficult, but basically how that's done is we calculate the precision and recall at various IOU thresholds. So in the beginning, you say, at an IOU threshold of 0.5, what is the precision and recall going to be? So if we go back here, at an IOU of 0.5, we're rejecting this box because it's only 0.4. That's potentially a valid classification, but we'll accept these two because they're above 0.5. From there, we can generate the precision and recall and generate a precision and recall graph. And like I said, we want to balance them off, right? We want something that balances both the relevance of our detections and the qualities. And the way that's done is by trying to get this graph to move to the top right. And so we can measure that by measuring the area under this graph. And that's called average precision. The greater that area, generally, the better we're doing in terms of that balance. Then we do this for every class and every IU we're interested in, and that gives us the mean average precision. This is a little bit of a misnomer. It says average precision, right? But we are still using recall, so that can be misleading, but it does include both, which is quite a nice quality. So sorry, a little bit dense. The equations are simple, but I even find it difficult to get an intuitive grasp of what they mean. The thing I want you to take away is that when we're talking about object detectors, we're looking at mean average precision for performance. And that mean average precision is this nice balanced metric that determines both how relevant and how good quality our predictions are, as well as their bounded boxes. It's simple, it ranges from 0 to 1, so it is easy to interpret. Higher is better. With said, you'll often see it reported in the community as a percentage, so just times by 100. So, now that we know, basically, we've got a rough idea of how to rank algorithms, we can put that to use, right? So here are some state-of-the-art object detectors. And when I say state-of-the-art, it is quite cutting edge. The majority of these algorithms are less than a year old. So when you're looking at the output from big companies like Efficient Det, that was made by Google. I think the people who came up with YOLO originally, I could be wrong, but they might have been working with Facebook. You know, there's a lot of heavy weight behind the development of these. They're always trained on urban data, so there's big urban data sets with lots of classes, lots of images behind it to create these useful algorithms. So there's a bias there that I'll talk a bit towards the end. But the important thing to note is that in terms of mean average precision, the state of the art within the past year is getting between about 35 and 55 mean average precision. So, you know, the tech giants, they're not reaching these sort of blazingly high figures like 90. But I've got to say, I mean, it is quite difficult to get high figures like that. The other thing you can take away from this graph is on the x-axis here, we've got latency, so that's basically the speed it takes for a graphics card to process an image. Obviously, as you come further up to the right here, it's getting slower and slower. So if you choose any one architecture, each of these points represents a bigger network. So we can not only just choose an architecture, but we can size our network to our needs. It's not represented in this graph, but implied is that each of these dots going to the right is a bigger architecture. So the cost of having a bigger architecture is slower inference, so less frames per second, but better performance. So this gives us a little bit of choice. Ideally, we want to push to the top left. That would give us the highest performance and the best speed. But you know, there are constraints like the size of the network that will tend to slow you down. So I'll talk about how we applied this. I was hoping Guy would have some of the images of the data that we used in this experiment. He did have some. They were taken in wheat and chickpea, in cobbity and narrabri. And we were looking for annual ryegrass, turnipweed, and sow thistle opportunistically. When I say opportunistically, that's because we had a lot fewer labels in sow thistle than we did for turnipweed and ryegrass. We tried 3 different architectures. So YOLO V5, this is less than a year old. Efficient Det, this is less than a year old. And faster RCNN, it's sort of a golden oldie. I mean, it was developed in 2015, so it's not that old, but it was one of the first algorithms to do well. So we sort of used it as a benchmark. We tried across a couple of different image scales and a couple of different architecture sizes, but I'll get to that. I suppose the last thing I should add is the ranking isn't entirely arbitrary. I've ranked them from architecture size. So at the top, YOLO V5 extra large is a huge network, 90 million parameters, down to the small YOLO, which is only about 7 million parameters. And you can see generally the smaller you go, the faster the throughput of your images. So this is what we're getting. 60 frames per second in terms of detection. So, easy conclusion. Again, having gone through the mean average precision, you know this is a way to rank algorithms. Bigger is better. The YOLO V5 architecture was reaching 0.3 in terms of mean average precision. This is sort of at the bottom edge of the state of the art. Remember that slide I showed you before? All the algorithms within the past year that are, say, 35 to 55. And we can talk about that towards the end. So if we choose one architecture and we change the input resolution, we get the intuitive result that using a high resolution image is better. So here we've jumped from 0.27 mean average precision on a 640 by 640 image to 0.3 mean average precision on a 1024 by 1024 image. And that's quite a nice improvement. Similarly, for any given architecture, if we keep the image size constant and just make the architecture bigger, so here we're using a small YOLO, here we're using a large YOLO, again, intuitively, we get better performance. The interesting thing I think about this is if you look at the jump from 0.27 to 0.28, I mean, it's minuscule, right? So that tends to suggest that depending on your application and your needs, it may be better just to use a smaller network with high resolution inputs. And I should also add on top of that, again, because we're using this very large network, 90 million parameters, we're only reaching about 40 frames a second, whereas if we use a smaller network with high resolution images, still slower than the small network with smaller images, but it's faster than the large network with small images. It's a bit wordy. So decomposing the results. Turnipweed did quite well. We're getting mean average precisions of between 0.4, so the high end there, and 0.6. So this is in line with the state of the art. This means it's easier to detect weeds with rarely obvious signals, so broadleaf weeds, than ryegrass. So when we look at ryegrass, unfortunately, the detector did not do so well. It's lagging quite far behind state of the art. And again, I'll talk about this in the conclusions. It's a difficult problem. Grass versus grass. I mean, ryegrass looks very similar to wheat in imagery. So some qualitative examples. We've got, so for our best network, the small YOLO with high resolution images, ground truth on the left, so these are labels that no doubt I generated, and then the output of the algorithm. We've got reasonable detection of ryegrass clumps. That's a nice, easy to detect signal. Here we've missed a ryegrass in the ground truth image. That's occluded by some of the wheat. Still reasonable. Like I said, we got good performance on broadleaf weeds. So here we've got turnipweed. You can see it's got quite confident predictions. So 88%, 97%, 92%. Another one, quite nice. But it's not perfect, right? We can see that through the metrics. Sometimes it does things that I just don't understand why it would miss them. So there's a nice bulky ryegrass clump here that's labeled in the ground truth, yet the algorithm missed it. Intuitively to me, it seems like a very clear signal, yet the algorithm didn't pick up on it. Also, there's a teeny tiny turnipweed there, missed by the algorithm. One of the problems you have is you can't run these images through these networks at full scale. You need to downsize them. And then they get downsized and downsized and downsized in the feature encoder. So if you have teeny tiny objects like this, they often fall below what you might call the receptive field of the network. They basically become invisible. So perhaps not ideal, but I'm a lot more comfortable with this than I am with that. Again, missing large objects that seem obvious. we'll have to investigate why that's happening. It seems like an obvious thing for the algorithm to pick up on.
Do we have a confidence interval?
So that's another thing. You can choose what level to cut off your detections. So I have chosen 0.5. Intuitively, that means there's a better than 50% chance that it's correct in its detection. It is possible with these big objects, could investigate that they're falling below that threshold. Where was it? That threshold of 0.5. So if it returns a confidence of 0.4, do you want to treat it as a ryegrass? And it's a valid question. When we spray, how confident do we want to be that what we're targeting is the target we're interested in? And that's something that I think would be good to get feedback from the community.
So actually, that missed one in the middle is the potential that it was in 4 different acquisitions of below 0.4 in 4 frames.
Well, it's interesting. I mean, now that you mention it, we do essentially have a video feed. So I didn't put those slides up here, but you will see strange behavior like this slide in, say, frame 1. It's missed the weed. In frame 2, it's got it. In frame 3, it's got it. Maybe in frame 4, it's dropped it. You could possibly smooth over that by doing tracking. That way you can keep a more stable hypothesis of what's actually in the field. But yeah, I mean, like I say, kind of comfortable with small objects. With larger objects, I don't find that to be as nice an icon as we would like.
So we do have a comment from
Yep.
Arnold online. He says, my thoughts for less reliable mean average precision for grass. If you ask 2 people to label a golf ball with abandoned box, they would be in near perfect agreement. If you try the same with a ryegrass weed, they will likely be very different. That leads to mislabeling and weak training data sets. There is a lot of subjectivity in labeling amorphous or diffuse objects like grasses versus less diffuse objects like Southwism.
Spot on, Arnold. So, I mean, that is one of the things I was going to get to in conclusions in terms of labeling data. It's, like Arnold says, label a golf ball, it's very obvious. I'd say it's the same with broadleaf weeds. You can see where the boundaries are, you know when to end it. If you go back to things like ryegrass, with these large clumps, it's still, I think you could find a boundary. I think you could still say we can extend the perimeter reasonably comfortably and contain the whole ryegrass clump. One of the things that's difficult to do is when you have ryegrass that's just emerging or merged, it can be hard. What do I label both blades as the ryegrass, one blade as the ryegrass? When it's clumped together, is it just one big clump? Do I try and demix it into 2 ryegrasses, if I can see that? So labeling consistency is a big deal. These algorithms are only good as the input you give them. And so we do need to pay attention to what is important to the application. I'd say in applications like this, maybe philosophically, it's not the right tool. Perhaps we want to go somewhere else. The difficulty here, and I suspect it's a lot of these images pulling down ryegrass accuracy, well, I shouldn't say accuracy, performance, I mean average precision from at least the clumps, is these blades look even more like the wheat at this stage of growth than the clumps of ryegrass look like wheat at later stages. So this is a very tough situation for the algorithms.
Actually, you can on the return on investment aspect of it, like how much time you can invest in these things to really hard to improve on, or out the requirements.
Absolutely. Look, I guess the engineering approach is we like to make useful things to a specification. So you will try to solve the need that's easiest and most urgent out there. I'd say, you know, for things like broadleaf weeds, I think technology is pretty mature at the moment and could provide, I think, useful performance out there. With grass versus grass, you're right, it's going to be much greater investment to get to a point. you know, is that where we want to be spending our money? I guess that's for the industry to answer. But certainly, it's certainly one of those things that has to be traded off. Like I say, I think the barriers are low for broadleaf weeds. We're almost there.
Asher, you say that, and that's a logical conclusion about broadleaf versus grass, but that south is look like it had very low detection. Am I reading that wrong? Around 0.1.
Which one?
South Thistle?
Oh, yeah.
Slightly dark, yeah.
So, yeah, I glazed over that. This is also part of sort of the conclusions. I said we collected South Thistle opportunistically. I can't remember the numbers, maybe you've got a better handle on it, Guy. I think it was something like 1,500 labels, 100 labels, and then 200. Like there was a big difference. So it really just got drowned out by being a minority in the data set. But my hunch is, quite strongly, if you balance the data sets, you should see the same level of performance as this. What you might see is a bit of confusion between the two. So if differentiating species is very important to you, there might be a bit of a disadvantage there. But I would expect that you see similar rates.
Yeah, so Guillaume has commented, love your presentation, Ash. I think it covers lots of questions and issues we've been having and still have. For instance, what are the key metrics to assess algorithm quality, how to correctly annotate a patch of ryegrass, etc. And he also says, by the way, for the grain industry, I think recall is actually called precision.
Really?
Terminology is slightly different there.
Look, it's an interesting note. One of the things I realized working with Guy is there is sort of an overlap of concepts that use different words for various things. So I think Guy found that in the weeds community, detection and localization, those words have slightly different meanings to the computer vision community. So yeah, look, I think different name, same concept, but certainly precision and recall are worthwhile to optimize. So, I mean, touching on some of the comments and just to wrap up, we can possibly have more questions after that. So why the gap in performance? So we saw that the best that the algorithm could do was 0.3 mean average precision. That was largely due to broadleaf weeds, where ryegrass pulled the performance down. Again, compared to the current state of the art, so between 35 and 55 mean average precision. So all of these algorithms that we've used, it's called transfer learning. We take them, they're pre-trained on all this urban data that I talked about. So you've got all the computing power of Google or Facebook or whoever it may be. They publish the weights of this model. You can then retune it to your data. The problem with that, well, I mean, there's a lot of benefits you save on computation, but a possible problem with that is you inherit this bias where the detector is being built from the ground up on urban scenes. If you think about urban scenes, they've got usually quite distinct colors, they've got very hard edges, discrete shapes. It's very different to the messy kind of tangles you can get in agriculture. And we need more data. So this analysis was done on a small subset of data. It was, I think, 2,000 images around about. That's not a lot in the grand scheme of things. When you, again, look at these algorithms and what they're trained on hundreds of thousands of images. More data will allow us to draw more confident conclusions. Other things we're seeing, things that we are actually seeing, not things that we think we're seeing. It would allow for scratch training. So like I say, we could possibly take these algorithms, train them from the ground up, see if by removing that bias for urban scenes, we can increase the performance to be in line with what they're getting on urban data sets. And it also allows us to potentially design new algorithms if we find that there's something intrinsically difficult about agriculture, which might be possible. I mean, I think wheat and ryegrass is a very difficult problem to solve. It might require a new type of algorithm architecture. And this sort of underpins some of the motivation for something like Weed AI. By having community access to data, it does allow people to start validating, training these algorithms, trying new formulations. So I think it could be a very powerful resource for not just the research community, but also getting the IP and methods out back into agriculture and production. That's it for me, guys. Questions?
There's one comment.
Yep. So Joel has commented that in the workshop this time last year, there was a discussion which concluded with the decision that whilst recall and precision are both needed, precision is more essential because recall could be achieved by repeated application during work.
I think Dion was talking about how precision was more, so recall was more important than precision. Because recall, if you got a low recall, missing equivalence, like grow up at seed, where precision is about not spraying the crop. So, and I think that discussion point in my mind seems to change depending on the industry you're in. So, how much does the crop work, and how much is a weed stake with it.
And probably weed control technology.
Yeah.
No, that's exactly right. I mean, you do at some point have to make a, I suppose, a value judgment on what the effect of false negatives and false positives are. If it's okay to miss a weed and quite damaging to destroy crop by accident, you might want to go one way. If you don't want to miss weeds and you're willing to risk a little bit of crop damage, you can go another way. So certainly getting feedback from growers on what their sort of tolerance is in that balance, I think would be quite useful. Certainly not the case that, you know, we design things to completely strip fields of crop, but, you know, if 1 out of every 100 square meters you've got damage, is that acceptable? 2, 10?
I think actually in the first instance, going to start using these technologies in the crop, we're probably going to be using selective herbicides.
Yeah.
So, which is what builders are doing now. So, yeah, it doesn't matter if the crop quality, it doesn't matter about getting the wheat cut. Assuming you're using carbon amaranth, yes, which everybody always does.
Well, that's it, right? So I guess this goes back to the weed control method. If you are using a selective, then you can push for a high recall. That way, you're never going to miss your weeds. And if you have some spray onto the crop, because it's selective, it's not going to be a disaster. So yeah, I mean, that's where discussion comes in and trying to figure out what the right priority balances are.
So the background to the work on the open source database, Weed AI, I hate to keep harking back to this conversation. So I was at a weed conference 2 years ago, I think, when Guy and I were listening to the Bilby people talk about their weed image processing and data collection, exercises, etc. And I think Guy asked at the end of the presentation that, along the lines, well, you know, can we access that data? And the response was absolutely not. And that's fair enough. It's a company that's investing in developing a weed recognition tool that they want to use to deliver weed control technology to growers at a cost. And so our discussions then were about, well, right, so all these companies are doing these developments independently. They're collecting their own data sets, they're annotating those data sets, and they're developing their own algorithms independently. those costs by targeting high-value cropping systems, horticultural systems, or corn, soybeans in the US, Europe, etc. How can we get this technology into Australia without just trying to beg and plead these companies to come and develop their systems here? And it's probably going to be a low return on investment opportunity. We figured that wasn't going to work, so we felt that we really needed to potentially create a system where we could facilitate the development of technology by perhaps doing a lot of the groundwork with the image collection and annotation processes. That, hopefully gets the weed control industry in Australia interested in the development in crop cycles of weed control technology. And with that, I'll just introduce Henry.
Everyone.
Works with the Sydney Informatics Hub and is going to talk about the development of the Weed AI database. Henry?
All right, thanks everyone. So just as a brief introduction about what we are at Sydney Informatics Hub, basically at the University of Sydney, we're part of what's called the Core Research Facility, and we're a group of data scientists, software engineers that provide support for researchers like Michael, Guy, and Asher in data analysis and developing infrastructure, such as in this case. Oh, that's great. Cool, great. So to help introduce really the context of Weed AI and why it's something that we think will be helpful for the grains industry, I'd like to pose kind of a question. So I'm from the United States, and if we can develop a model that can detect weeds in wheat in, say, somewhere like Texas, can we take this model and apply it to detect weeds in wheat, say, here in Wagga? Can we take a model that's been fit on detecting weeds in canola crops? Can that be applied to the same to wheat as well? Can we take a model that's been trained on images taken in natural light? Can we apply that in images taken in artificial light? This is really one of the important things. This is what we think is the core of what Weed AI is creating this diverse set of images, because Asher presented a lot of interesting results that we've had from special data sets that we've collected. But with machine learning algorithms, really what we want is we want models that you can transfer and take to solve your specific situation. Because like Asher said, most of the machine learning models that have proven to be so successful for things like detecting cars or people in urban environments, they've been trained on thousands and thousands of millions of images that are collected from a diverse range of scenarios. And to get this same sort of success in detecting weeds in the diverse range of cropping environments that people have, we need to have a really diverse data set that captures just all the immense range of conditions that people have at their own unique farms. So what exactly is Weed AI? So Weed AI is the open repository of weed imagery. And so there's a couple components of it. So first off, we have this common standard for annotating weed imagery. And I'll cover this very soon. We also have a system and bits of infrastructure that we've developed for storing this data and making so that it's there and people can access it. And finally, we have a website and an interface so that users can view the data, they can search for data, they can download the data, and they can hopefully, ideally, upload their own data. And all of this, the goal here is that we're going to make it easier for people to develop models to detect weeds in people's crops in all sorts of situations. So that's the goal here. All of this is built around creating the most diverse, most high quality, and just the largest collection of weed imagery out there. And so I'm going to begin by providing a little bit of an introduction about this common standard that we've developed for annotating weed imagery. So the reason why this is so important is we want to make sure that when people upload data, that it can be kind of like interchangeable. Think about it kind of like, something kind of silly like Lego bricks, for example. There's a specific, standard that those bricks are made for. They always will fit together. So the people who are working with those bricks, building their toys and stuff, can always put them together. The same is what we want with these weed images. We want anyone to be able to upload data, to be able to assemble their own data set that's useful for their own, growing scenario. We want to make sure that every bit of data that's stored in there can be interchangeable. And we also want to make sure that people can easily find it. We want to make sure that it's accessible. We want to make sure that people can mix and match and create whatever they want. And also, we want to make sure that all of this data is fully reusable. So say, for example, Asher's or Jiang or one of our colleagues has developed some amazing model that performs really well at detecting turnipweed in wheat crops. We want to make sure that if somebody else wants to apply that model, they can then take it and they can test it and get the same performance. They can see, oh wow, this actually is as good as they say. So this is why this common standard is so important. And so this next slide is really for the computer vision and computer people here. So if this gets a little crazy, don't worry about it. So basically our standard that we've decided to use here is Weed Cocoa is an extension of a really popular format for annotating computer vision images. That's called COCO, which stands for Common Objects in Context. It's been developed and used by these big entities like Microsoft and Facebook. But basically, the core thing here is that COCO supports info-rich annotations. So there's lots of information that you can store there about what is in those images. And also, it's just widely used. So there's already existing infrastructure out there so that it's easy for people to store the data, to annotate the data, and then also to convert it into other formats that they might need to use in an actual machine learning pipeline. So you've heard YOLO a lot. So YOLO is another format that's used for storing computer vision annotations. It doesn't contain much information. So a standard like COCO provides a lot of info and ability to store info that you may need to know. Hey, is this data right for my problem? And then once you've determined that, you can then decide to actually convert it into another format and use that for your actual machine learning application. So what if we added on to COCO to make it into Weed Cocoa? So one of the things that COCO has is this concept of what a category is. And so a category basically is whatever is in that image, right? So the way we have decided to represent categories is combining both the role of the thing that is being annotated or labeled and the species. So in this case, we have these two pictures. So in that picture on the right, we have, this is a crop and it's wheat, right? So we have the crop, wheat. So that's the role as a crop and it's wheat. Then in this picture, we have what's being annotated here is the wheat, but it's now a weed because it's a volunteer crop in a canola field. And this is a photoshopped image, I know, but basically the whole concept here is we wanted to support the ability to make it so that if somebody wants to look for just images of a plant as a crop, they can look for that, or they can look for that plant if it's potentially as a weed or as a volunteer. So we basically wanted to represent the fact that plants can serve multiple different roles depending on the particular situation. If someone's interested in pictures of volunteer wheat, they're probably not interested in pictures of wheat as a crop. That's basically why we have this representation. The other thing that's really interesting about COCO, and the reason why we went with this standard, is that it supports the potential to add more levels of categories and sort of add in a hierarchy. And so the reason why this could be useful is we can incorporate the actual taxonomic hierarchy for each of the things that we're annotating here. And so the reason why this might be useful is, imagine, you're interested in, say, controlling turnipweed, right? You can decide, hey, I only want to find images of turnipweed. But what if you decide, I want to look for images of all broadleaf weeds? So then maybe you can decide, hey, I want to look at images with brassicales, which is basically broadleaf weeds that you might want to find. So that's one of the really useful things about COCO is it supports these potential extensions we could add so people can search and find just the images that they want, or they can even go, all the way down to specific and just look at individual species, like wild radish, for example. The other big thing that we've added onto COCO in making Weed Cocoa is this thing that we call the agricultural context or the ag context. And so basically what this is it contains three big components. One of them is a whole assembly of crop information. And so this is info that will help the user decide, is this data set relevant to my problem? And so it's stuff like the growth stage of the plants that are in the imagery. It's information about the soil, information about the ground cover, if there's stubble or not. Basically, it's anything you need to know to decide, hey, is this right for my particular weed problem? And to know that if you can actually use that for it. The other thing that it contains is a whole section on photography information. And so this is really important for the people who are developing the site-specific weed control technologies, because this would contain information on how the pictures were captured. So say if you're developing some sort of technology that's going to be mounted on a boom spray, you might be interested in images that were captured from some sort of scenario kind of like that. And you might be less interested in images that were captured with a mobile phone. And so that's what the photography section includes. It includes information so you can know, is this data right for my problem that I'm trying to solve? And finally, it contains information about the weather. And so this is important, of course, because with any imagery that we're using for training machine learning models, we want to have as much control as possible on it. And images captured when it's cloudy are going to look really different from when it's bright and sunny, or images captured in the morning are going to look really different from later on in the day because the shadows will be different. And so this can really influence the performance of the models. So we want to make sure that we have all of the information that is needed so that a user, when they go on Weed AI, they can look and they can find the images that are just right for their problem. And finally, one of the other features that I just want to touch on really quickly here that we have supported with Weed Cocoa is these schema.org dataset compatible metadata. And so the reason why this is so important is basically it makes it so that it's pretty easy to cite the data, and it's pretty easy for users to be able to see who collected the data, to see who funded the data, and basically it supports the full citation of that. And also it just makes it easier for this data to be findable, just searching through Google, so it makes it easier so that Google can pick up this and make it easier for people to see the data that we have. And so I could spend a while talking about a lot of this infrastructure that we've built up over the last year to get Weed AI live, but I think it's probably more useful to instead actually do a little bit of a live demo.
Share the screen.
Okay. So he's going to change the screen sharing for the people who are viewing from home. Oh yeah, you can bring it up. Yeah. So it's just if you just look for Weed AI, I think Guy's showing the link there. It should be in a browser. Did it go?
I think I need to get onto that screen first.
Yes, that's the one we want.
Yep. Up on there, and I'll just share.
Excellent. Yeah, let's just share the screen.
Okay, there you go.
Excellent. So this is it. Welcome to Weed AI. So when you go to Weed AI, what you first see is you just first see basically an unfiltered, all the images that are currently on there. And so this is primarily imagery that's been captured and curated by Guy and our colleagues at the University of Sydney. And you can see that there's a couple of filters. So basically you can look at all the images that are there, and you can see the little bounding boxes there. That's showing you what is being annotated in those images. So in this case, it's you see some broadleaf weeds in wheat, and this is seedlings. Now let's say if I'm looking on here and I'm like, well, actually I'm only interested in chickpeas. I'm growing chickpeas. I'm not interested in looking at images with wheat. So you can then filter and see, hey, this is stuff that's annotated in chickpeas, right? It's like any other sort of thing that online, like you can filter and look by anything. So right now we have a couple different filters that we've implemented, things that we thought could be useful. But over time, we're going to probably change this and add more filters depending on what people like yourselves find are appropriate or useful or interesting to filter by. You can filter by the distance. So I know, so let's say I'm a farmer or a grower in Narrabri. I always spell Narrabri wrong. and I want to look for things that are only within, 10 kilometers of Narrabri. And now I can filter by that, and I can see that location. And I chose Narrabri because I know that's where a bunch of these images came from. Yeah. Great. So let's say I'm the chickpea farmer or grower. I always get that wrong. And I want to look at this data set now. Right? So I've decided this is a data set that's relevant to my situation, right? So then I can just click to see the data set, right? And so what we see here is we see a description about what the data set is. You can see who created it. You can see Guy created it. You can see the license. And I'm going to touch a little bit more on this, but currently all the data sets we have in Weed AI are with the Creative Commons CC BY 4.0 license, and I'll talk about that a little bit more. And we can see that this is funded by the GRDC. See information about what is annotated in there. You can see it has ryegrass, wild radish, and sow thistle. Thank you. Sorry, I'm not a weed scientist. All right, and we can see that it's bounding boxes, segments. There's no segments in there. It's just bounding box annotations, and we can see how many images for each, right? Then we can see this information about the crop. We can see it's chickpeas. We can see the growth stages of the crop that are in these images. See that it's gray soil, that there's a cereal surface cover, and we can see an approximate location of where these images were taken as well. You can see information about the type of photographic equipment that's been used to capture these images. And you can see information about the weather. And so then if you decide, hey, this is relevant for me, you can then download the data. And this basically, what it'll do is it will download a zip file on your computer, which contains all of these images from this data set in the full resolution that we have in our Weed AI database, as well as one of our Weed Cocoa annotation files. So that contains all of the information about the images, the things that are being annotated in there, the agricultural context, as well as licensing information and other stuff that's, with metadata that might be essential to getting proper attribution for this data. And then that can be converted and used for developing machine learning models. So let's say, what if you have a data set that you have and you want to upload it to Weed AI, which we would love. That's what we want, is for people to have a data set and upload it here, right? So we currently have support for uploading. Right now, basically, if you have images that are annotated in either MS Cocoa or our own Weed Cocoa format, you can upload them straight away, and it's pretty easy. We have tools for making your own agricultural ag context here. So you can click on this link, and there's a handy tool that is mobile compatible for creating your own ag context that you can then save and then use when you upload your data, because that's required. You can also construct and save the metadata. This is the stuff that's required to make sure that you and your collaborators and your funders get properly attributed for the data. So this is really critical. And then basically, yeah, you need the annotations to be in MS Cocoa format or our Weed Cocoa. And we can, if you're interested in this and you need assistance with getting it like that, we can talk more about that later. But we have developed some importers, and we're looking at adding in more features to make it easier for people to get their data into Weed AI. And so that's what we have for now. Slides again. Sure. So you can look at this on your own computer. You can look at it on your mobile. I would recommend looking at it on a computer if you can, but it works fine on the phone as well. Excellent. I'll skip ahead. All right, back to where we were. Great. So now I'd like to spend some time with you guys talking about the future and the next steps for Weed AI. Because really, our number one objective, the number one thing that we can provide to people is, diverse imagery. And so really we want to encourage people to upload the most diverse, the most high quality, and just the most images possible. Because we want to be able to support people developing models for every single possible situation where you may need a model to help you implement some sort of site-specific weed control. So currently we have planned out a little bit of a development roadmap for how we can expand on and continue to add features and improvements into Weed AI. So the first category of things that is a sort of broad continuing support and just continuing to make Weed AI better, and we've already implemented some of these things, and my colleagues, particularly our software engineer, Zhang Li, he has been crazy working. He's just busy working on adding in more and more things into Weed AI, so good for him. He's excellent. Then we also have a broad category of expansions. And so this is where, at the end, I'd like to get a little bit more of you guys' feedback, because this is the sort of stuff that we're thinking about adding in, and we just want to know what would make this a better tool and something, like what would make it easier for people to decide, hey, I've got some pictures, I want to put them on Weed AI, I want to make it better. All right, so continuing support. So we have, like, these are just general improvements that we're looking at adding in. So first off, we want to make it easier for people to contribute, to put their images on Weed AI. So first off on that, we are looking at adding in more guides and more documentation. Just basically stuff to make it more clear about what you need to do to put together a data set so that it can be put on Weed AI and how you could potentially start benefiting from that. We want to provide, as part of this, we want to provide more support for more formats in the uploader. So if you're not familiar with computer vision, there's many different ways that people can annotate images. And we already have developed some converters to convert from different annotation formats into ours. And now we're looking at trying to add in those converters into the upload process on the website that we have right now. We also just want to add in some general usability improvements, make the website clearer, make it easier to see what's going on, just make it a more user-friendly experience in general, like you would with any website. We also want to provide some support for more licenses. Because this is a really critical thing, because not everybody will want to trust their valuable IP to anyone. And so this is something that will probably require a lot more discussion over time and a lot more thought and investment in. It's just deciding, what all licenses do we want to support? How do we want to handle different types of licenses besides the CC BY 4.0 license? That's a really easy license to deal with, but to support the broadest possible collection of data, we really need to think about how we can support other types of licensing for imagery, because not everybody is going to be completely comfortable with uploading their valuable data, and just letting anyone use it for free with attribution. We also want to make it easier to, just as a user, for you to find data that is relevant to your problem. And so we're going to provide some more options for how to search for the right species, or adding in multiple levels of taxonomy, like I showed earlier with the hierarchy there. And we also want to think more about how we represent growth stage, because that's a really important thing, because, images of crops that are young are going to be very different from images that are from crops that are much closer to harvesting. And so we really want to make sure that it's easy for users to find images that are relevant to their particular scenario. So in terms of actual expansions or additional content that we're interested in adding to Weed AI, we want to support other types of imagery. So currently we allow we only have visual light imagery. So this is images that are captured with standard red, green, blue cameras, right? But there's other types of cameras that are used, that capture things like the near infrared channels. So we want to provide support for multispectral imagery, because that may potentially be useful for some types of site-specific weed control. Also, we want to try to provide some way to represent the train and test data splits. So this is really critical for the machine learning side of things, where let's say someone has a model, right, that they've shown, hey, this gets some amazing whiz-bang performance on the data. Well, then if someone wants to go take that model and take a look at it and decide, does it really get that performance? They need to be able to then test it on the same data split that was used in whatever paper when that model was published. This is all part of encouraging reproducibility with the science that's going to be made using Weed AI. We also would be interested in adding the ability to add additional annotation layers after the data has already been uploaded. So let's say Guy uploads some pictures with bounding boxes, and then down the road, somebody decides, hey, I'd like to go and take a look at those images. and add in segmentation to segment out each of the individual little parts of the plants on there. That would be an interesting feature to add, and it would probably make it a lot easier for people to improve the quality of data that's on there. But one of the other things that we really need to focus on expanding with AI is ensuring that the data is high quality. Because we want diverse data, we want a lot of data, but we also want this data to be the best data possible. And so there's things that we could think about adding in to ensure that the data that's on WeedAI is good and actually accurate. And so some of those features could be adding in like user rankings to rate like, is this image a good image or a bad image? Is this image what the image, is what is annotated in this image, is that accurate or not? And then also potentially the ability to add in, for users to add in comments, like just commenting on things to see, like just to provide their feedback on what's being shown in the images. And this kind of leads into the next area of expansions that we're thinking about for WeedAI. So this is about building up a community of users and people who are contributing to WeedAI and benefiting from WeedAI. And so some of these things that we can include are things like challenges and benchmarks for data sets. And so the reason why this could be something that would really help WeedAI is the fact that in the machine learning world, people are attracted to difficult challenges. If they see a difficult problem, people are going to start to get excited about developing a solution for it and coming up with models and coming up with competitions and trying to fight to see who gets the best performance. And so there's a really famous website, Kaggle, where users are able, where people go in there, put their data sets on there, propose a challenge, and then teams from around the world compete. And they can see who gets the best performance possible, typically for a prize, but sometimes just for the glory. And so adding in features like this to WeedAI could help encourage machine learning researchers and engineers and teams from around the world to start looking at this tricky problem, trying to identify grass from grass, and finding solutions. Because that's a hard problem. And we need to show people that, hey, this is something that you should get excited about trying to solve. Another thing is that would help for the whole community building is just reporting the performance that is obtainable on the data sets that are on there. So if someone goes and looks at the data on there, they can see, hey, someone's been able to get a model with this performance on it. I want to see if I can do better. Or they might think, oh, hey, that's got really good performance, so I'm going to take that data and use it for my own model because it's a good data set, right? And as something to help support this broader development of machine learning algorithms on the data on WeedAI, one feature that can help is adding in just ways that when you are viewing the data set, you can just click a button and then instantly start interacting with the data in a Jupyter notebook or some other online coding environment where you can start to test things out and interact with it. And that just would that's basically the whole idea there is to lower the barrier of entry so that people don't have to do as much to start seeing the types of gains they could get from using data on WeedAI. And so really now I've introduced some of these ideas that we have for continuing to support WeedAI and continuing to develop WeedAI and expand on it. But now really the question is, what should be our priority? Which of these would be the most useful or should we focus on the most in order to help grow WeedAI to get the most diverse, high quality, and just the most images possible? And so the reason, just to reiterate once again, the reason why this is just so essential, the diversity, the quantity, and the quality, is because we want to make sure that machine learning algorithms developed on crop imagery aren't just going to do well only on the images that they were trained on. We want to make sure that these models will be able to be transferable to different scenarios so that someone can take a model and then apply it to their own situation that's not just the images that the researchers use to build the model. We want people to be able to take it and apply it on the ground to their own situation. So that's why this is so important that we have the most diverse, best, and most images as possible. So we really need diversity in a lot of things. We need diversity in the types of crops. We need diversity in the types of weeds that are there. And we need diversity in the growth stages of the plants that are being shown there. We need diversity in the soil, diversity in lighting, diversity in the camera equipment. Really just we need diversity in everything, and we need more. So yeah, that's about it of the structured thing here. And so next, I really think it'd be good to get some feedback from everyone about what would help people to contribute, to start putting in images so that we can start growing this database.
So it's not just about getting images.
Yeah.
We can all do that.
Oh, yeah.
It's the next step about annotating those.
That's-
images. So I think that's the barrier, particularly of those categories that you use.
Yeah. All right.
Like how easy is that? Like it seems pretty difficult when you're showing.
No, it's not complex. It's just you want to invest time. And so I see those images. You go back to Weed AI, Henry.
Yeah.
And we're basically those images like on my phone. I think load one afternoon, set it up, like in like a few hundred pieces, and upload them at night. So that'll go to 40 months. So you can do a handful like that. Like the one in the center left, center right, top right. Second to the left, sorry. So you do those. But yeah. Yeah.
Can I clarify the process here? Because I'm not going up with it and doing, but it also seems like there was some
I think that that's probably just because the images are being displayed on the website's front end. We're rendering the bounding boxes there, and sometimes it might not be really easy to tell that they're there or not. All of the images that have been uploaded to AI are annotated and have annotations associated.
maybe thank you too on anyone more able to
Okay. Yeah. Yeah.
So maybe you make why don't you contribute where the sort of expertise and where you have access to kind of do what I'm
Yeah, that's an interesting thing to think about because so one of the things is that currently we don't have a way to really represent the annotation effort or to sort of like show the annotation consistency. And so that starts to become a little tricky when we start thinking about crowdsourcing or adding in more people annotating. So if I take a data set that Guy's uploaded, I know that Guy has been the only one doing the annotation. But then as soon as we start adding in more people, it might become a little more complicated. And I think for a feature like that, we really just want to make sure that we provide extremely clear user guides in how to make proper annotations. Yeah. Regulation, yeah. Yes, that's a really good question. So that's one of the, where we were thinking about how to really deal with that. That's where the user rankings might come in, or user ratings might be a good feature. I think it is tricky to think about how you ensure that all of the images in it, especially if it's bigger. Yeah.
There's a lot. I mean, I know there's probably a lot of existing crowdsourcing.
Yeah. Yeah.
So yeah, that's an issue, but maybe it's been answered.
Well, so one of the first things is that currently we are requiring when people upload the data that they must have the full, complete weed cocoa annotation. So they need to have that. So that already kind of hopefully screens out some people who may decide to, if they are wanting to troll us and upload things that are actual weeds. That should hopefully discourage that a little bit because then they, I don't know if anyone really wants to invest in developing an agricultural context for that stuff. But I think one of the things to consider with that is that to provide really good moderation of it as well, like with many other online data sets, would require just more funding for continuing support for that, like people to actually go in there and moderate it. That is something to consider because, I mean, yeah, there are existing solutions to this sort of problem, but it is a really tricky one because it's, okay, so say for example, some of the really famous urban data sets with like millions of images, that's taking, most of those are trawling images from things like Flickr or other commonly available image hosting websites. So those images have already passed whatever community guidelines those websites have, and then are then collected and collated by that institution. The thing that's different with Weed AI is that we are making it, we're not going out there and collecting all the images ourselves. We're supporting users being able to upload their own images. And so yeah, that is a really difficult problem to solve, and how, and to think about is how to make sure that data is all high quality, all complete, and all abides the same quality standards. I'm very happy to get suggestions for how to do that.
So
easily.
We do have a comment from Joel related to this online. Upload and annotate later requires much higher infrastructure costs too, assuming a larger scale of low value images were uploaded.
Yeah.
And I think we also do have a, I think Liam wanted to ask a question. So we'll see if we can just unmute Liam.
Yep. What people in the room will be familiar with a product called Coleman. It's run by the same guy who cracked the PlayStation. He startup where you can run a car off a mobile phone, basically. So think autopilot, but on a mobile phone. He runs basically this thing called a comma 10K. And basically what that is it's 10,000 PNGs of real driving. So just a bunch of images. And he takes the general public to, or at least people who are interested, to go onto the GitHub and then actually do the labeling on these images. And basically the system will just get slightly better as people keep improving that slight accuracy on each and every labeled image. That way you've got, hey, here's 10,000, we're going to start with this and we're going to work our way onto finishing that one. And then we can then start moving on to another data set. The idea in this instance is the data that is collected in that 10K data set is actually a very wide distribution of data. And that means that you're not just saying, oh, we've got nothing but broadleaf, we've got all types. And that will be very, very helpful, at least that in my mind. What objects are they annotating? Basically, like this is a car, this is a road, this is a tree, stuff like that. They have a very simple classification model. So, you know, here's a road lane, here's a truck, here's a car. I'll put the link up so people can have a look at it. There we go. That's simply what they're doing for autonomous vehicle stuff. You can imagine kind of how that can get translated into the more open weed AI kind of policy.
Do you want to comment on that?
I guess one of the things I would comment on is that I think what's kind of tricky here is that for the types of data that we'd be uploading to Weed AI, it might become a little tricky. So if we have images of wheat with ryegrass in there and we want to get annotations, like, I don't know about you, but if someone shows me a picture of a car on a street, that's pretty easy to annotate. There's a car on the street. Or, hey, there's two cars on the street, or there's a stop sign. Those are things that we're all used to seeing all the time. But the people who are used to seeing ryegrass and wheat are primarily going to be growers and agronomists. And even then, it's a pretty tricky task at times looking at images depending on the resolution. So I think that getting some sort of like online crowdsourced thing would be excellent, but I think it would be a difficult thing to really properly encourage and moderate. You need to think a lot about how to best really do that, because it's pretty hard to tell the difference between ryegrass and wheat from some of these pictures. Particularly, I mean, maybe if the ryegrass or the other weed that's going to be there is not occurring in the actual crop row, but if it's occurring right there with the crop, then it's tough. It is a really tough challenge.
So Liam has a response to that. He says he 100% agrees with that, that this wouldn't be targeted at the general public, but it would be sort of aimed at farmers, growers, and researchers involved in these science.
Yeah. And then I think Joel has a comment as well there.
Yep. So Joel says, not that we should be afraid of crowdsourcing, but we might need to support annotators by kickstarting it with lots of data and a pre-trained model to support what Guy called targeted annotation.
Yeah, from an agronomist perspective, I think the contribution, you've got probably a lower history of let's say people into your agriculture camera.
Yeah.
On a more regular basis than before. So I'm not sure it's around the age, but the how it can be different that's probably why what they are just getting out of computing this data set
I mean, time. So. Yeah.
And we spend more time in days than ever before, and we take so long.
Yeah. Yeah.
Coming up with market strategy, so to speak, and how we engage with the industry.
Yeah. So I guess there's two things there that I can see that would be really important then. So first, like you said, would be making sure to show that there's a benefit. They're going to get something out of this. Maybe not immediately, but like down the line, it's coming. They're going to get a benefit. But I think one of the other things to think about is that with the imagery that we want to have on WeedAI, I think that to support people easily capturing images that are going to be really useful for the developing machine learning algorithms, we need to make sure that there's some sort of like standardized way to do it. So I don't know if Guy showed any of those pictures of the sort of thing that he was wearing. He has this backpack with these like cameras walking around there. I'm not expecting everyone to just whip out one of those, but the thing is that we want these images to be kind of approximate to the sort of technology, like we want them to be captured in the same kind of way that they may be captured by the technology that's going to be implemented using those models. Yeah, so some sort of like standardized some sort of system, just a way to make sure that, you know, yeah.
It's really just providing that platform. So
yeah.
Yeah. Make photos that he wants at the time from the current requirement, but then you can well, it's easy to go, right, I'll stick up here and every wall gets analyzed and take a photo and take that.
Okay. All right. So learn from them, basically, is what you're saying. Yeah.
What would be a suitable motivation for a driver to train on themselves that have found images in their quick.code?
Well, from my perspective, just be part of the next generation of trials. Plan it out, their engagement is new.
The development of an algorithm for that group. They might have similar soil types or similar crop environments.
Yeah.
They teamed up together, flexibility, annotated it, and the recognition of it we got for from southeast of the
We're there, software. How do I, as we did, I'll start at taking photos tonight. So, how to do it. So that's the question. Yes, there's different ways you can do it. There's lots online, right? One of the big ones, language box, and maybe upload your website, and then you can big class of weeds and sound tools, and display the image, and then you go to the image. So if it's, I mean, yeah, you had a successful Google account, you know, the driver, so I was going to there's a need for some level of education or a need for online growth. We've spoken to the farming group, the front webinar, 10 growers come in, this is where the software is, this is how we run it, where you target 1,000 weeds or more, 7 or whatever it is.
Yeah.
Go for it.
So you probably have a little
That phone isn't working.
I have another question which.
Sorry, Eric, there's a couple of questions that are really closely related to what we've just been talking about. First off, Andrew suggests that we have a community of approved annotators. I guess training comes into that as well. That could annotate the uploaded images, and yeah, that would circumvent the issue with the golf ball analogy that we had earlier on. And Guillaume suggests that we could almost have a review system. So yeah, there's problems with peer review, we know that in science, but if we have secondary reviewers looking at the annotations after they've been uploaded as well.
Should add there's a review system as part of the platform.
Yep.
I think having a review like the other way to do review possibly is you can do like you assign the same data set or
Of it to multiple people, and then if you have agreement on certain labels within your bounds, then you accept that label. If not, it's rejected, sent back. That's what we're doing.
All right, so I guess we've got a lot of ideas about what might be needed to make people want to contribute to AI. And one of the questions was showing why they should.
So that leads directly to the next sort of discussion slide is like, I guess what features would help you and how could we better show that you can benefit from Lead AI? Aside from satisfying the plant nerds. Yeah.
Understanding of what's coming.
Okay.
In terms of the technology and how much this can improve that technology that's coming.
Yep. It's a perfect time. There's a lot of discussion about this type of technology. If you were ever going to try and get something that's off the ground, now's the time. People would be interested in commit and help. The key piece of me is with any of these things, it's about making it easy. The fundamental basics of, as soon as we start talking about that, cut all that out, right? All you need to do is put a red box out the door, because that's simplistic technique to get to a broader populace. It's going to be important to get that significant volume going.
But perhaps if you like you think of the Canada app, you actually have an app already developed with Lead AI, so it takes all that, gets all that, you walk in, the red box goes over the lead, growth stage recording, bang, the process. The annotation was really short. Yeah, that's true. But in the background of that, you have data very populated, it's your app, so all those data.
That's right.
The data associated with you.
I look at the amount of information you're chasing in terms of, but I understand completely what you've got to have. But straight up going, holy smokes, that's a lot of effort. Very hard. So whatever you can do in that context, repopulate.
Yeah. Okay. That makes sense. Yeah.
So I think we should learn from the drone example. There's a really good discussion online recently about the frustrations with the drone mapping. We're always with some clients recently who've done it with a particular provider and really poor outcome from a big investment. Yeah, a lot of interest out there.
I think the other piece there that you've got very setting expectations. It's great to talk about this technology, making sure that there's not an expectation tomorrow we're going to see something. So, set the expectation for the contributors that yes, you can perform great performance, but you're probably not going to see something from it tomorrow.
Well, what were the pain points with the drone? Was it the interoperability?
Yeah, very good drones. Sort of two main commercial providers. see that between the two providers at the same price.
Mhm.
But it's a, it's like expectations are really we could have solved.
So we do have a comment from Joel. Was a conclusion from a previous discussion that there are people willing to annotate and there are people willing to capture photos, but they can and should be different people.
Yeah.
We need 10 more dice.
Any other ideas or discussion?
I did have one other thing that's not related to this.
Okay.
My time, but I don't have a feel for this, so I'm just going to throw it out there. The people who are building the machine learning, maybe they have a wish list of situations that they want. For example, your very first slide there was wheat in a crop of canola that need to eat there, but you need very specific training sets to address that. So, I would guess that there's very strong seasonal variations in what kind of photos that people can take. So, the researchers throw out something like one wheat in canola, and see if we can do that. So then we'll get a million photographs. Maybe a wish list from the researchers.
I'm sure it's targeted. So you get a broker, we want ryegrass, it's 3 leaf, whatever.
Okay, so basically some way that, people can, post their like shopping list of what they want to.
We have like individual items, maybe like specific items that can then be uploaded or downloaded.
Yeah, that could be something like that, or even just like in the data sets view, just allowing us to see like what all data sets are available for each problem.
Right. So perhaps an advantage of that is that taking photographs like that already satisfies the first level of detection. Here's a folder of photographs containing 3 photos.
Yeah. Okay.
The first stage is
That's a good idea. No, thanks. That's great.
I'm just like,
I think already from a grains industry perspective, there's some really low hanging fruit. Like Jason was jumping here, there's economic studies being done around wild radish in wheat in WA.
Yeah.
So it's a massive cost to grow it, and then you move to the northern region. So the turnip is particularly expensive. So set priorities within the industry already that are the lowest at the hanging fruit and the biggest return on investment for this my collection of data and then potentially the tech to manage it.
Okay.
But ryegrass in wheat for me is such a low price. That doesn't even rate. We don't even try and kill ryegrass at all. Turnip and chickpeas, that's massive. So if it's harvest capacity, it's a big great contaminant.
Machine learning.
We target the normally it's 0.
Ryegrass is tough.
It is, but it's you manage it appropriately in the right touch. You can lots of controlling ryegrass, but I'm not interested from a growth perspective.
Yeah, we're using helpful to keep ryegrass numbers wrong. It's definitely and it's very hard to find good ones. And when you see some of those bigger ones that you had up there, almost beyond control, you come up with a laser guide and laser beam. There's nothing herbicides that are going to pull it down and cry.
So just going back to Jules' comment about having 2 separate groups of people taking images and annotating. Andrew has commented, I think they should be different because decoupling them would offer the potential to increase the database more quickly and to a higher standard, assuming the annotators vet the images and the sound good.
To be honest, if I had high quality images of certain weeds in crop, I'd be having a lot of safely. But you do lose on the standardization. Yeah. So it's really trade-off.
How much are the cameras?
So then I guess then you can perhaps look more towards projects where you fund groups to collect images specifically.
Sorry, that's ryegrass in week last year. So fantastic.
Put a box around it, Greg.
It's a beautiful grower has a meal on his head, so it's really unique circumstances. There's no chemistry or control. So there's so many good images out there. So an army of plant nerds. Yeah. And I think the other big selling point is that this is independent. There's no commercial online. So I think you've got to sell that. I certainly do. It's a commercial guys, but it is certainly what's done.
I mean, on that
Australians
point,
pride themselves to agree with having that.
I guess that ties in with licensing. Do you have a few stance there?
But for me, that's something that counts in my mind is the intent where you're sourcing some of this imagery from. Yes, okay, you've got independence, great. No issues with it. If it feels that it's broader economy base, you've then got nutrient and others who are a foot in the door in some ways, and some of this, I don't know, or speculating that maybe some of the challenge. There's plenty of others, so it's not, I don't think it's a independent licensing is definitely something.
I guess at the moment, all the value for lots of these companies is in the data, and perhaps after a while, the value shifts to the product itself. And maybe it doesn't become much of an issue, but maybe that's a bit of an idea.
Plus, it's probably a question for someone, at some point in the future, do they see releasing their data set once they've got something up and running?
But these are all CC by 4.0, which means they can use commercial names.
Yeah.
But I think that's, to me, keeping it open as possible. As soon as you start to narrow it, and just
All right, well, I think that's probably about time for some questions.
Sounds like a good idea, Henry. All right, that was excellent, Henry.
yeah,
Great.